Hello all. So in this session, I'm continuing Carnot's engine. So here in previous session, up to this we completed. That is we got eta efficiency. That is this is the equation. So now next from adiabatic process. So what are adiabatic process conditions? We have PV per gamma is constant, TV per gamma minus 1 constant, P per 1 minus gamma into T per gamma is constant. So from this equation, TV per gamma minus 1 is constant. So previously, so if we observe Carnot engine, Carnot cycle, so this is isothermal expansion, adiabatic expansion, isothermal compression and adiabatic compression. So now I am considering adiabatic processes. So here this is the adiabatic processes. So if we observe here the process in the adiabatic process expansion, so temperature is changing from T1 to T2, and here compression temperature is changing from T2 to T1, right? Yeah, T2 to T1. So therefore, so T1 to T2, T2 to T1, in that volume also V2 to V3 and V4 to V1. So now using this, I am using this second equation, TV per gamma minus 1 is constant. So T1 V2 gamma minus 1 equal to T2 V3 gamma minus 1. Next to T2 V4 gamma minus 1 is equal to V4 V1 per gamma minus 1. So that if we cross multiply and if we do some rearrangements, we will get like this. So but adiabatic expansion ratio, that is V2 by V1 equal to V3 by V4 equal to rho. So therefore, so from this V2 by V1 equal to V3 by V4. So I am substituting here V3 by V4 equal to V2 by V1, so that V2 by V1, here also we will get V2 by V1. So this V2 by V1 all are cancelled, so that we will get T1 minus T2 by T1. So that is T1 minus T2 by T1. So from that eta is equal to 1 minus T2 by T1. Okay. So this is the final eta equation for heat engine Carnot cycle. That is, if we observe this is the case for a reversible heat engine like Carnot's engine. Eta is equal to 1 minus Q2 by Q1, that equal to 1 minus T2 by T1. If we observe this 1 minus T2 by T1 equation is only for reversible heat engines, then what about irreversible heat engine? So for irreversible heat engine, the equation is only 1 minus Q2 by Q1, not 1 minus T2 by T1. Okay, so this equation holds good for all types of equations, that is reversible and irreversible. But coming to reversible, we can write 1 minus T2 by T1 also. From that, T2 by T1 equal to Q2 by Q1. Okay. So here some points we have, that is for a reversible Carnot engine, eta is equal to 1 minus T2 by T1. Efficiency is depending only on the temperatures of the source and sink. Okay, so it is independent of nature of working substance and area of the Carnot cycle. So efficiency అనేది only temperatures పైన depend అవుతుంది, that is on the source and sink temperature, but not depending on the working substance and the area of the Carnot cycle also. So here we know that is rho, adiabatic expansion constant, V4 by V1, V3 by V2 equal to rho. So from this we can write here, if we observe this is V2 by V3, this one, in this we can write 1 by rho. So T2 by T1 equal to 1 by rho we will get here. So T2 by T1 equal to 1 by rho per gamma minus 1, so that eta equal to 1 minus T2 by T1. So in that place I substituted 1 by rho into gamma minus 1. So this is the efficiency equation. Efficiency eta is equal to 1 minus 1 by rho whole per gamma minus 1. So here we have some problems. So find the efficiency of a Carnot engine working between ice point and steam point. Sorry. So ice point is what, 0 degree centigrade. Steam point means what, 100 degree centigrade. Okay. So T1 is equal to 0, that plus 273. I am converting into Kelvin scale. So 273 Kelvin. And T2 is equal to 100 degree centigrade. So 100 plus 273, that equal to 373 Kelvin. So he asked the efficiency of Carnot engine. So eta is equal to 1 minus T2 by T1. So 1 minus 373 by 273. Sorry, 1 minus T2 by T1 only. Sorry. Okay. T1 means it is a source temperature. So this is T1, this is T2. T2 is sink temperature. So to 273 minus 3 by 373. So 373 minus 273 by 373. So 100 by 373. So which is less than 1 only. Okay. So next, eta of Carnot engine is 1 by 6. If its sink temperature is decreasing by 80 degrees centigrade, its eta becomes 1 by 3. Then find T1 and T2. So eta is equal to 1 minus T1 by T2, that equal to 1 by 6. Right. Next, T2 value is decreased by 80 degrees centigrade. So eta dash is equal to 1 minus T1 by 1 minus T2 by T1. Yeah. T2 minus 80 by T1. So I'll write here 1 minus T2 by T1 minus 80 by T1. So this value is what? 1 by 6. So it becomes 1 by 3. So 1 by 3. So 1 by 6 minus 80 by T1 is equal to 1 by 3. So that 80 by T1 is equal to yeah, here we will get plus 1 by 3 minus 1 by 6. So 80 by T1 equal to 1 by 6. T1 equal to 80 into 6, 480. Now T2 is how much? From this I'll write eta is equal to 1 minus T2 by T1. So 1 by 6 equal to 1 minus T2 by 480. So T2 by 480 is equal to 1 minus 1 by 6, 5 by 6. So T2 equal to 400 degrees centigrade. These are the T1 and T2 values. Okay. Next, third law of thermodynamics. So third law of thermodynamics, that is unattainable statement. Okay. Unattainable statement. So what is unattainable statement? That is third law. It is impossible to reach absolute zero temperature, that is 0 Kelvin, in any finite number of operations. That is what. So 0 degree centigrade means 0 Kelvin means minus 273.15 degree centigrade. So we can't attain this much lesser temperature. So that is the third law of thermodynamics. So absolute temperature is 0 Kelvin, that is minus 273.15 degree centigrade. And also one more definition, a sink temperature at which eta is equal to 1 is called absolute zero temperature. Okay. So this is absolute zero temperature, a sink temperature at which eta is equal to 1. And one more triple point. So triple point temperature is 0.01 degree centigrade, where 3 phases exist, and triple point pressure is 4.6 mm of Hg. Next, Carnot theorem. So what is Carnot theorem? All reversible engines working between same temperature limits have same efficiency. Okay, all reversible engines working between between temperature limits, that is T1 and T2. Anni reversible engines which are ఒకే టెంపరేచర్ లిమిట్స్లో వర్క్ అవుతున్న అన్ని టెంపరేచర్స్ యొక్క ఎఫిషియన్సీ సేమ్ ఉంటుంది. ఇంకా అదే లిమిట్స్లో వర్క్ చేస్తున్న ఇర్రివర్సిబుల్ ఇంజన్, రివర్సిబుల్ ఇంజన్స్ ఏమో సేమ్ ఉంటాయి, బట్ ఇర్రివర్సిబుల్ ఇంజన్ ఎఫిషియన్సీ అనేది రివర్సిబుల్ ఎఫిషియన్సీ కంటే తక్కువగా ఉంటుంది. నో ఇర్రివర్సిబుల్ ఇంజన్ వర్కింగ్ బిట్వీన్ సేమ్ టెంపరేచర్ లిమిట్స్ కెన్ బి మోర్ ఎఫిషియంట్ దెన్ రివర్సిబుల్ ఇంజన్. So eta is equal to 1 minus Q2 by Q1. This is for irreversible engine, and for reversible engine eta is equal to 1 minus T2 by T1. So So eta of irreversible engine is less than or equal to eta of reversible engine. So here eta is 1 minus q2 by q1, that is less than or equal to 1 minus t2 by t1, so that q2 by q1 is greater than or equal to t2 by t1, or q2 by t2 is greater than or equal to q1 by t1, or we can write here q1 by t1 minus q2 by t2 is less than or equal to 0. Okay, this is Carnot's theorem, right? So Carnot cycle ABCD traversed in reverse path becomes a Carnot refrigerator. So this is a Carnot. So this is first one, second one, third one, fourth one. So this is Carnot cycle, right? So if we reversely, if we go, we will get Carnot refrigerator. Sorry, we will get refrigerator. Okay. Next, already given these things. Next, very important one, entropy. What is entropy? So entropy is the measurement of disorder. So change in entropy ds is equal to dq by t. Okay, so this entropy is a exact differential equation. This equation is exact differential equation, and also entropy is a pointer function. Means what? It is path dependent, sorry, path independent. Now actually ds is greater than or equal to dq by t, very important. So this ds is equal to dq by dt. It is for reversible process, and ds is greater than dq by dt. Dq by t, it is for irreversible process. Okay, and one more very important, in reversible adiabatic process, entropy is constant. So many times this question came. In reversible adiabatic process, entropy is constant. Okay, so entropy is a extrinsic process, that is, it is a path dependent process. Okay, these points are very, very important. This is entropy definition, and change in entropy is equal to dq by t. So next one, clausius statement for entropy. Definitely one question compulsory, it will come in exams. So clausius statement, according to him, system plus surroundings equal to what? Universe. Now system's entropy, it may increase or decrease. Okay, next, surroundings entropy also, it may increase or decrease, but universe entropy is, it may constant or it increases, but it never decrease, never decrease. Okay, so in a reversible process, system plus surrounding entropy is known as isolated system entropy. Okay, so system plus surroundings, that equal to, will get universe. So system plus surroundings entropy is equal to isolated system entropy. Okay, so in reversible process, actually in reversible process, entropy constant, but in irreversible process, if ds is equal to 0, reversible, that is constant. Next, if ds is greater than 0, it is reversible process, sorry, irreversible process. ds is less than 0, it is impossible, right? So ds equals 0, it is reversible case, that is entropy is constant in reversible process, already given. Reversible adiabatic process, entropy is constant, that is ds is equal to 0. So ds is greater than 0, that is increases in irreversible process. Next, in cyclic process, very important, this is also previous question, dq by t is equal to 0, cyclic process. In cyclic process, integral of dq by t is equal to 0, that is change in entropy is 0. So next, in irreversible, this is reversible, irreversible cyclic process. Irreversible cyclic process, integration of del q by t is less than or equal to 0. This is called clausius inequality. Very important. So in irreversible cyclic process, del q by t, integration of del q by t is less than or equal to 0. This is called clausius inequality. Okay. So clausius statement for second law in terms of entropy. So what is that? All natural processes in universe takes place such a way that entropy of universe always increases. Okay, in all the natural processes of the universe, such that in all the processes entropy increases. Entropy increases. This is about entropy. Okay, so we have some points on entropy, that is so entropy and disorder. Entropy is a measure of disorder in the system. So here example, ice converting into water. So ice converting into water, so disorder increases. Ice is the ordered form of the water. So water is not ordered one, so that here orderness is decreasing. Okay, orderness is decreasing. So as heat increases, disorderness increases. Okay, so what is how disorder? As heat increases, disorder increases. Here latent heat, some points, latent heat of latent heat when ice is converted into water, that is 80 calories per gram. 80 calories of heat per 1 gram. Next, water to steam, latent heat of vapor 540 calories per gram, latent heat of vaporization. Okay, next, entropy and unavailable energy. As entropy increases, unavailable energy also increases, unavailability increases. Okay, ds equal to del q by t. As del q increases, tds increases. So here some points, as entropy of the universe continuously increasing, unavailable energy also increases. So energy is going from useful form to unavailable form. So this is called the principle of degradation of energy. Okay, as consequence, universe suffers a heat death ultimately. As heat increases, the unavailability increases. So this is called principle of degradation, and consequently heat death, ultimately heat death occurs. Okay, so this is about entropy and unavailability. So ground state is the most stable state and the most disorderly state also. Okay, calculation of change in entropy. So change in entropy in different cases. So first one is ds in heating or cooling a substance. ఒక సబ్స్టెన్స్ హీట్ చేస్తున్నాం ఆర్ కూల్ చేస్తున్నప్పుడు ఆ డిఎస్కి ఈక్వేషన్ ఏంటి అంటే, సో డిఎస్ ఈక్వల్ టు డిక్యూ బై టీ యాక్చువల్లీ. సో డిక్యూ అన్నప్పుడు సబ్స్టాన్స్ హీట్ డిక్రీజ్కి ఈక్వేషన్ ఏంది ఎంసీడిటీ. సో ఎంసీడిటీ బై టీ. సో దీన్ని ఇంటిగ్రేషన్ చేస్తే ఎంసీ లాగ్ టీ ఫైనల్ బై టీ ఇనిషియల్. దిస్ ఈస్ for substances. For gases, ds equal to ncv log tf by ti, and ds is equal to ncp log et. So in heat ncv dt, we got these equations for work, that is dq, du, we have ncv dt, like that. In that, if we do some derivations, we will get these final equations. Okay, so ds equal to ncv log tf by ti, also ds equal to ncp log tf by ti. Next, ds in first order phase changes. ఫస్ట్ ఆర్డర్ ఫేజ్ చేంజెస్ అంటే ఏంటి, మనకి వాటర్ హీట్ యూజ్ చేసుకునేవి. సో వాటర్ ఐస్ వాటర్గా కన్వర్ట్ అవ్వడం అలాంటివి. హీట్ ఎప్పుడైతే యూజ్ చేసినామో ఆర్డర్ చేంజ్ అవుతాం, ఫస్ట్ ఆర్డర్ ఫేజ్ చేంజెస్. సో డిఎస్ ఈక్వల్ టు డిక్యూ బై టీ. సో ఐఎమ్ టు లేటెంట్ హీట్ బై టీ. సో డిఎస్ ఈక్వల్ డిక్యూ బై టీ, లేటెంట్ హీట్ ఆఫ్ వేపరైజేషన్. ఇది మనకి ఫ్రీజింగ్లో. ఓకే, ds in heat conduction from let T1 to T2, heat is conducting, then in that cases ds equal to dq by t. So net change in entropy is ds equal to minus d1 plus d2 if we substitute that. Okay, ds in isothermal process, w equal to actually q into nRT, q equal to nRT log vf by vi. So q by t, so nr log vf by vi, isothermal process. Okay, these are some problems. So next one more, ds in free expansion. So ds is greater than del q by t. So irreversible though. The equivalent irreversible process is an isothermal expansion from vi to vf, and ds equal to nr log base c vf by va. Okay, so this is a free expansion case. Okay, so this is about entropy. And in next class we have topics of kinetic theory of gases, very important. TS diagrams. Next, monoatomic gases, diatomic gases, triatomic gases. In that cases, what are the degrees of freedom? See here. Next topics are kinetic theory of gases. Next, monoatomic, diatomic, triatomic. In these cases, what are CV values, CP values, and what are the relations, and how many degrees of freedoms. Okay, next very important one, Maxwell law of distribution of speeds. And next, thermodynamic Maxwell's equations we have, very important. Next class is very important, definitely 1, 2, 3 questions we will get from that topics. Okay, thank you.